In today's lesson, we're going to talk about solutions of linear systems by the Gauss-Jordan method. So you've probably noticed by now that we place our equations in alphabetical order, such that the following happens. We have x, y, and z in order and equal to a number on each one of our equations. When they are in that order as above, we really only care about working with their coefficients, which is the number in front of the letter, if you recall. We can write the above equations using a matrix. So I'm going to pull the coefficients from above. So my 2x plus y minus z equals 2. I'm going to have it as 2, 1, negative 1. I'm going to put this bar here. It's kind of our separation between our equation piece on the left. This could represent the equal sign and then 2. My x plus 3y plus 2z, grabbing those coefficients, 1, 3, 2, and 1. X plus y plus z is 2, gives me 1, 1, 1, and 2. And then I'm going to close my matrix. Each one of these pieces going from left to right is what we call a row. Each one of these pieces going up and down is what we call a column. And each item inside our matrix is what we call an element. This whole thing put together is what we call an augmented matrix. Just like our previous section in lesson 2.1, we can use operations to keep the equations equivalent. So we can do the following. We can interchange any two rows, so we can flip-flop them, but every element in that row needs to move all together. We can multiply the elements of a row by any non-zero real number. We can add any non-zero multiple of the elements of one row to the corresponding elements of a non-zero multiple of some other row. So we can multiply each row by a non-zero number. And at the same time, when we do that, we can interchange and add rows together, just like we did in lesson 2.1. This is an extension of the echelon method of solving systems. So what we're going to do is write the equation so the variables are in the same order on the left of the equal sign with the constant on the right, giving us so that we're able to write an augmented matrix. The key here, though, is to use row operations to obtain a matrix that has zeros above and below a diagonal of ones on the left of the vertical bar. We call this reduced row echelon form. So all of these, notice, in our diagonal are ones, and everything else is a zero, with just numbers here on the left, or excuse me, on the right. This would then correspond to a solution. Notice that this is our x, y, and z. So here we would see that since I only have one x, 0 y's, and 0 z's, I would say that x is equal to 3. And the second, I have 0 x's, 1 y, and 0 z's. So here I'd say y is equal to 4. In the bottom, I've got 0 x's plus 0 y's plus 1 z, so z equals negative 2. So once we get it into reduced row echelon form, we're able to easily pull the solutions straight from that matrix. So let's solve 4x plus 5y is 10 and 7x plus 8y is 19 using the Gauss-Jordan method. So first of all, I see that it's already written with all the variables on the left equals to our numbers on the right. I see that the variables are in order, so I'm going to turn it into an augmented matrix. giving me 4, 5, my bar 10, and 7, 8, my bar, and 19. So my goal, again, is to get the diagonals equal to 1 and everything else is 0. And because I prefer to leave my fractions until the end, I'm going to work at getting my corners into zeros first. And I like to work from top to bottom, working left to right. So I'm going to focus first on obtaining this part to be a 0. So to do that, I'm going to multiply my first row by 7 and my second row by -4. Notice when I do that, I'll end up with positive 28 and negative 28. So when I add those two pieces together, I end up with a 0. So when I multiply my first row by 7, I end up with 28, 35, 70. I multiply my bottom row by -4, so -28, -32, -76. I'm going to add these, and I'm going to say I'm going to add them down because I'm going to replace my bottom row with that 0, because that 0 is going to be where I want it to be within my matrix. So when I add these together, I end up with 0, 3, and -6. This is going to replace my bottom row. My top row is going to stay the same, okay, because I only can add and combine to make 1 here. So I'm still going to have 4, 5, and 10. My bottom row is going to be that 0, 3, -6. My next goal is to obtain this 5 to become a 0. And then I'll work on getting my diagonals into 1 values. So when I look at 5 and 3, I see their smallest multiple is 15, but one of them is going to have to be a negative, and it doesn't matter which one. So I'm going to multiply my top by 3 and my bottom by -5. You could do the top by -3, the bottom by positive. It doesn't matter. And I'm going to add up because I want to replace that top row with where my 0 is going to end up being. So when I multiply 3 across the top, I see we have 12, 15, and 30. I have 0, -15, and +30. Adding these together, I have 12, 0, 60. So I'm going to rewrite my matrix. My top row is now 12, 0, 60, and my bottom row stays the same. Now that I have my zeros where I want them, I need my diagonals to be 1s. So to do that, I'm going to divide my top row by 12, because 12 divided by 12 would end up with 1. I'm going to divide my bottom row by 3. So when I divide my top row by 12, I see I get 0, 1, and 5. And my bottom row, 0, 1, -2. My diagonals are 1s and everything else is a 0. Here I see then that I have x plus 0y is 5, so x equals 5. And I have 0 x's and 1 y is 2, giving me y is equal to -2. Writing our solution as coordinates, we have 5, -2. Let's try a 3 by 4 matrix. Our equations are all mixed up. We have x's and z's on the left, variables on the right. So let's start off by rearranging these so that all of our variables are on the left with our numbers and our constants on the right. And then at the same time, putting our variables such that they are in alphabetical order. So x, y, z. So when I rewrite our first one, I'll have x subtract y plus 5z equals -6. The middle row, I've got 3x plus 3y minus z is 10. And it looks like our bottom one is already wrote appropriately, so I'll just recopy that. All right, let's now convert this into our augmented matrix. 1, -1, 5, our bar, -6, 3, 3, -1, 10, 1, 3, 2, and 5. Again, we need to have our diagonals to be 1 and everything else to be a 0. I'm going to start working with my zeros first. I'm going to try to get this to be a 0. I'm going to work from top to bottom in this column and then move to the next column, working top to bottom, identifying where my zeros need to be first, and then changing and dividing to get, if we end up with fractions, have them at the very last. So if I want this to be a 0, when I look at 1 and I look at 3, all I need to do is multiply our top by a -3, and I see that I'll already have opposite signs. So when I multiply my top row by -3, I end up with -3, +3, -15, +18. We're not multiplying the middle row by anything, so I just recopy it down. And if you can add these in your head, that's awesome. I just like to show our work. Okay. And we're adding down, remember, because we want our 0 to be in that 3 location. So everything else will stay the same. Except our middle row is now going to be 0, +6, -16, 28, and our bottom row is still 1, 3, 2, 5. My next target is to try and get this 1 to be a 0. Again, if I look at my top value, it's already a +1, so I could multiply either the top or the bottom by -1. Just one needs to be the opposite sign for us. So when I multiply by -1, ideally it's just going to reverse all of our signs. We didn't need to multiply the bottom row by anything, so I'm just recopying it so that when I add, again we're going to add down because our 0 is going to be in that location of our 1 element. Giving us our new matrix, copying everything that we didn't change or make changes to. And our new bottom row is 0, 4, -3, 11. Now when I look at this, I want to try and obtain this -1 is my next target to obtain a 0.